Hello. In this lecture, we will discuss the rotational spectra of non-rigid rotor. In the previous lecture, we have discussed the rotational energy levels of a rigid rotor and the transitions between them give rise to rotational spectra having peaks at 2B, 4B, 6B, 8B, 10B, 12B, etc. with an equal spacing of 2B centimeter inverse. But the experimental data of rotational transition of HF shows a variation in the value of B. You can see in this table the theoretical value of B is 20.56 for all the transitions by the equation B equal to H by 8 pi square IC. That is, the lines are equally spaced by 2B, that is 41 centimeter inverse, nearly 41 centimeter inverse. But the experimental B value shows a decrease in the value of B with the increase in the transition. That is, it would not have a constant 2B separation predicted by the equation of a rigid rotor, but it decreases steadily with increasing J. If we calculate the bond length of HF using each B values, we would get an increased value of bond length as the transition level increases, as B proportional to 1 by R square by the equation B equal to H by 8 pi square IC, where I equal to mu R square. So, as B decreases, bond length increases. It shows that our assumption of rigid bond is only an approximation. In fact, all the bonds can be elastic to some extent. At low energy levels, the bonds remain almost stationary. What happens at higher energy levels? At higher energy levels, the molecule rotates rapidly and the centrifugal force gets increased. That tends the atom to move apart. Also, the higher energy levels, as the distance between levels in the higher states increases, the frequency of microwave change to IR region, that is the nearest high frequency region of microwave, and it leads to vibration of molecule along with rotation. As a result, stretching of bond takes place. Hence, for a non-rigid rotor, the Schrödinger equation for energy levels may be written as Ej equal to Bj into J plus 1. This is the expression for the rigid rotor, along with minus dj square into J plus 1 square centimeter inverse, where d is the centrifugal distortion constant. This is the distortion constant as a result of centrifugal force, increase in the centrifugal force, which is equal to 4b cubed by omega square, where B you already know it is the rotational constant, and the omega is the vibrational frequency of the bond, which is equal to 1 by 2 pi root of k by nu. Frequency, it's the frequency of a harmonic oscillator. We were studied in the plus 2 classes or in the degree time when we are studying the spectroscopy. We have passed through the vibrational frequency of a simple harmonic oscillator. As the vibrational frequency is very small compared to rotational constant for small j, that is, for small values of j, the centrifugal distortion constant is not much pronounced, and thus the correction term dj square into j plus 1 whole square is almost negligible, while for j values of nearly 10 or more, it becomes significant. From this figure, we can compare the rotational energy levels and the spectra of non-rigid and non-rigid rotator. There is lowering of rotational levels as the level of transition increases, and also the spectral lines come closer. Since in most cases the higher energy transitions are rare, because most of the time population of higher energy level will be less. So we may have to use the rigid rotor model in almost all cases where there is lower transitions. So I am concluding my lecture of non-rigid rotor characteristics. Thank you very much.